Hello everyone. So in this video we're going to talk about the second of our three cases that I'm going to talk about. We're going to focus on in chapter 10, and that is pooled T inference. Okay, so as a broader picture inside of chapter 10, we're still in the situation where we have independent samples. So we're talking about two sample inference. We have two different samples, and that sort of means that we're looking at two different populations. And so in this case, we have two independent samples, meaning that one sample is not dependent in some way on the other sample, okay, which was just the same as the last time, okay, in the first video. And so we're looking at inference about the difference of two population means, the exact same thing as we were looking at in the first unpooled sample inference case. Okay, and the samples that we take are very similar, or they're exactly the same in the exact same manner as the last time. We take samples of the same size, of different sizes, possibly N1 and N2 from each population respectively. So we take samples possibly of different sizes from each population that we're looking at. Okay, so we have our samples in the same manner that we did in the first case. But here's where the differences happen. Okay, the assumptions are that we have independent samples, which was the same as last time, but this time we have equal variances. We have equal variances. What does that mean? Or equal standard deviations, you could think of. That means that hypothetically, we believe that each population has the same spread. Okay. We also believe that the population distributions are approximately normal, so they're normal distributions with the same standard deviation. So if you remember, if you're watching this video right after the first one, you'll remember. If not, I had a first toy example that I was working with that asked the question, do sophomores or juniors have higher GPAs? In this case, we believe that the distribution of sophomore GPAs and the distribution of junior GPAs are the same. Okay, so we have to believe that they're both approximately normal and with equal variances. It doesn't mean that they're exactly the same. They could have different means, but we believe that they're spread out the same. Okay, which can be a viable assumption if it makes sense, but it's often not the case. So if I had to say which one is most popular, it's probably the first unpooled case. Okay, but in this case we have equal variances, and so with that extra information we can do something more, or maybe something better than the last time. Okay, it may not necessarily be better, but we can do something different. We can try to take advantage of this fact. Okay, so when we have equal standard deviations, and so equal population standard deviations, sigma 1 and sigma 2, we can what's called pool the standard deviations together to get one estimate. So instead of having two sample standard deviations, S1 and S2, we're going to have one common one. So you might ask, why would we do this? Why would we take all this trouble? And you'll see in the next few builds here, like what kind of trouble that we're into. It's nothing really bad. The computer's going to do all the computations for you. But still begs the question, why would we do this when we have the other case? If we can pool the standard deviations together, we can get a more precise estimate. And so our confidence intervals are going to be smaller, and our hypothesis tests may be less conservative than the unpooled case. Okay, that may be good, or that may be not so good. When you're actually doing this sort of inference in real life, you have to take these things into account. But if we can say that we believe that the two population standard deviations are the same, then we can what's called pool the standard deviations together. And so the pooled standard deviation, it looks like this. So instead of having S1 and S2, we now have this common S, which is some sort of formula that takes into account S1, S2, N1, and N2. You'll see over on the right, okay, or in the middle there. So that's the pooled standard deviation. And so the standard error, what we're going to work with is this. It's that pooled standard deviation S times what is close to what we saw last time, but instead of the S1 squared and S2 squared that we saw in the first case, those S's came out in front to form that 1S, and then we have the square root of 1 over n1 plus 1 over n2. Okay. So again, we can make a confidence interval for the difference in means, the same general form. The confidence factor is still a t like it was the past two times. Alpha is found the same. The degrees of freedom are much nicer in the pooled case. Okay, in that unpooled case, you'll remember there's a Welch-Satterthwaite formula that was just really not fun to look at. Okay, here it's much nicer, n1 plus n2 minus 2. Okay, and so then we get a confidence interval, which is very similar to the last time. All that's changed is the subscripts of the t, and then now we have this common pooled S in our standard error calculation. All right, so that's confidence intervals. Hypothesis testing is going to be exactly the same with those very slight modifications. So we're still looking for the difference of two means. The null and alternative hypotheses do not change whatsoever between pooled and unpooled t inference calculations. Step 3, level of significance, exact same thing. The assumptions are almost identical. The only thing is that we now assume equal variances, which is an important part. The critical value changes slightly in that the standard error is no longer what it was in the unpooled case. It now has this form, which we talked about in the last slide. Okay, great. The p-value, exact same. The exact same way that we calculate it. And then the decision and conclusion, again, are going to be similar to what we're used to. And of course, this type of inference is what we call a pooled inference. And so the hypothesis test or significance test that we're doing here is called a pooled t-test. Okay. And so there's the summary for the confidence interval and hypothesis test for a pooled t-test. Okay, so I'm going to finish out these slides with the last section, section 10.4. And section 10.4 talks about dependent samples. So this is our very last case. And so as the name might infer, we are going to now talk about dependent samples. We're still interested, so we in theory still have two population distributions. And so we still have mu1 and mu2, which are the means of something from each population. But now these two populations are dependent in some way. So you'll notice in that very first build, in the very first sentence, I call mu1 minus mu2 something different than I have done before. I call it mu with a subscript of d, okay? Mu of the difference. Mu of the difference. And so that'll become important in just a second. The samples that we take are slightly different than last time. This time we take samples of the exact same size. So both samples cannot be of differing sizes, in this case, from two populations that have some similarities or are dependent in some way. They are often called matched pairs, okay? The observations that we take. So what type of similarities could I be talking about in this dependent or matched pairs case? So the first type of similarity that could occur is that the observations are taken on the same person. Okay, so that could be over time, or just at two different times. So maybe I'm in an education setting and I'm giving the students a pre and a post test. If I wanted to make inference about, so I gave the students a pre-test of how they understood graphing a linear equation y equals mx plus b. Then I implement some new and crazy idea about how to teach graphing y equals mx plus b, and then they take a post-test about what they understand about y equals mx plus b. In order to look at the two samples, pre and post, they are dependent in some way because the same student is in either sample. And so what I have to do is I have to match up those observations because there's some sort of dependence in there. And so that means, why would I have to do that and not treat it as independent? Well, if I have a really smart kid who already knows what's going on, those scores are going to act differently than someone who had no idea what's going on before there. And so to not match them would be not very smart on my part. Okay, so they could be the same person is in both, or the observations are taken on twins or some people who have some genetic similarities. So maybe I'm trying to test some drug, or I'm giving something to the human body. If I have twins, they're going to react probably in the same way, okay, or they might have sort of the same kind of reaction because they share some genetics. And so I've got to take that into account, or observations are taken on people with similar characteristics in some other way than twins. And so that could mean that they were in the same environment when they took the measurements, so on and so forth. They could both have high blood pressure when I'm testing some blood pressure medication. Okay, so those are different similarity types. This is by no means an exhaustive list, but they are the common ones that you see. So we take a new sample, okay? We have our two samples, and what we do that's different than the other two times that we did our sampling is that we take those two samples and we create a third column. Okay, if you were thinking of this in like an Excel sheet or some kind of sheeted data set, I take the first sample, I subtract the second sample from it, and that gets me another column, and I'm going to call that the differenced column, or X sub D, X bar sub D. And what you do in a dependent case is that you treat that as the one single sample. Instead of treating it as two different samples, you take the difference and you treat it as one sample because they're paired in some way. So essentially there's only one sample sort of thing there. So the assumptions of this case are that the samples are dependent, and the second case, the second assumption is that the differenced population is approximately normally distributed. So before we had each of the populations were normally distributed. Now we're only interested in the differenced population. Okay, so that might be kind of weird to think about. And also a third one that's always in here are that the samples were random in some way. Even with the dependence in there, they were still random. So there could have been random assignment, random something or other that's involved. Now, when we try to do inference on this dependent sample case, you take that differenced data, so X bar sub D, okay, which is found by the mean of the differenced data, and you treat it like one single sample. Okay, so like I said before, you have one column, you treat it like that's the one sample that you have, and you do the stuff we learned about in chapters 8 and 9 to do the inference. Okay, so you use the methods that we talked about in chapters 8 and 9 to make the confidence intervals and hypothesis test for paired inference. Okay, so that ends this slide and the set of lecture notes. So hopefully that made some sense. I will post another video that goes over actually how to do this, all three cases, in Minitab, and StatCrunch will follow along with Minitab. They'll do the same sort of thing. Thank you.